Let's now do some relativity examples that look at length contraction or time dilation, or perhaps a mix of the two. The first one we're going to be looking at is a 2009 exam question. It's specifically examination 1, back when there were 2 sets of exams. We've got an astronaut Benji is floating freely in space when Joel's spaceship passes him at a high speed. I think we can assume from the context of the question, or maybe from some information later on, it's probably relativistic speeds. Benji is holding a ruler and can see through the window of the spaceship that Joel is also holding a ruler. The two rulers are parallel to the direction of motion of the spaceship. That means we definitely are going to expect length contraction of that ruler, because it's parallel to the direction of motion. Both Benji and Joel measure the length of their own ruler to be 1 meter. Each can see each other's rulers. Benji observes Joel's ruler to be 0.6 meters long. So Benji measures Joel's to be 0.6 meters long. Remember, Benji is not measuring the proper length of Joel's ruler. From Benji's frame of reference, Benji is stationary and he sees Joel moving by at, it must be a relativistic speed because he's measured a significantly contracted length of that ruler. The question actually asks us though, which one of the following gives the length of Benji's ruler as observed by Joel? Well, let's now transport ourselves into Joel's frame of reference. Joel, in his frame of reference, would measure his own ruler to be 1 meter long. And from Joel's frame of reference, he's stationary and Benji is the one that is flying by. He'd be flying by at whatever speed Benji measured Joel to be travelling at. This is another example of length contraction, but it's really important to note we've got some strange distractor answers here. We've got answers that are larger than the proper length, and they can never be the case. They're just distractors that are trying to get you to try and think of some sort of reciprocal relationship. So we know it's got to be a contracted length, that means shorter than the proper length. So that also gets rid of this answer, because that's the proper length. It's going to be 0.6, and it's because the length contraction, whatever Benji notices with Joel, well, from Joel's perspective, Benji is travelling at the same speed that Benji measured Joel. It's all relativistic. So, he's going to notice the same length contraction. Who's right? Well, they're both right from their frame of reference. Continuing on with this question, it says, which of the following gives the proper length of Joel's ruler? Well, as we mentioned, the proper length is the length measured in a frame of reference which is stationary to the event or object of interest. So, if we're looking at the proper length of Joel's ruler, Joel is stationary in the reference frame that the ruler is in. They each measure their own length of their ruler to be 1 meter, so it's got to be 1 meter. Which of the following gives the speed of Joel's spaceship as measured by Benji? We're in Benji's frame of reference. Let's consider the length that he previously mentioned. He measured Joel's ruler to be 0.6 meters, whereas the proper length of that ruler was 1 meter. We can use the relationship that L equals L naught over gamma to determine what the value of gamma is, and that's going to help us with our ultimate goal of determining the speed of Joel's spaceship as measured by Benji. So, rearranging this, gamma is going to equal L naught over L, which is 1 over 0.6. You might recall in a previous lesson we did a derivation for the formula that I've just put here, the velocity in terms of c, and with gamma inside of this certain fraction that we had here. I had a couple of different rearrangements for this, but I might as well just use this one here. So v is going to be c, and it's great to have that c there because all of these answers are in terms of c. And it's going to be 1 minus 1 over the gamma value, so that was 1 over 0.6, bit squishy, squared. I guess I don't really need that set of brackets here, do I? So let's go ahead and just determine what's going on inside of that surd. It's a little bit yucky, but with our fraction template, we can manage it fine. You might have noticed that 1 over, and then in brackets, 1 over 0.6 all squared. You could do some reciprocals there. That's perfectly fine. Or you can just work with what you've got on your calculator, typing it in exactly. Alrighty, I get V equals 0.8 times C. You could have had C times 0.8, but algebraically that's kind of gross. So that gives us our answer of C. I've just realised I should specify, I mean option C. where the answer is 0.8 C, not option D where the answer is C. That's kind of confusing. This answer here, 0.8 times C. Let's read this next question very carefully because some people have difficulty determining which frame of reference measures the proper length and proper time with these kinds of questions. We're told we're looking at one of the basic particles of nature called the tau meson. It can be created using beams of high energy particles from an accelerator. When created, the tau meson has a very high velocity, given by this, and they've very kindly told us the Lorentz factor is 20. However, it only exists for a period of 6.0 by 10 to the negative 12 seconds from the scientist's frame of reference. After this time, it decays into two other particles. During this time, it is observed to travel a distance d. The figure shows the creation and the decay of the tau meson in the reference frame of the scientists. So these are the scientists hanging out watching it. They've measured this distance d, and they've measured this time here. Before we get into this question, it's asking for the lifetime of the tau meson as measured in its own frame of reference. Let's note down some things we've got here. Number 1, this time. This is the time measured by the scientists. This is not the proper time. This time is t, which is the dilated length of time. The proper time would be measured from the tau meson's frame of reference. T naught would be measured from tau, that's the symbol for the tau mesons, tau's frame of reference. So we can see we've got a dilated time here. That distance though, that is stationary with respect to the scientist's frame of reference. So this would be a proper length. So that means from the tau's frame of reference, they would measure, tau's frame measures contracted length. So that's really important. So again, the tau meson is going to be measuring the proper time because imagine the tau meson with a teeny tiny clock. That clock is going to be traveling with that meson. Now yes, a clock at that size doesn't actually make any physical sense, but it's helpful for this thought experiment we're doing here. Now the tau meson would see that length of ground or the accelerator or whatever it's traveling through moving past it, so it cannot measure the proper length here. The proper length is measured by those scientists who are stationary with respect to the ground. So it might be a little confusing here. We've got two measurements that are given. Well, D isn't a measurement. I imagine we might need to calculate that later. We've got two quantities here. One is proper and one is not. So really important to think of who's carrying the clock, who's carrying the ruler, basically. The question actually says, what is the lifetime of the tau meson as measured from its own frame of reference? That would be that T naught that we spoke about. So, we're going to have to do a couple of things. In order to be able to find T naught, we're going to need to know the value of gamma. They've very kindly given us that. So we don't need to do any more work there, but we do need to be able to find that proper time. So let's go into our equation here. Okay, so as we mentioned previously, T naught is given by T, the dilated time, divided by the value of gamma. So the time they previously told us, 6.10 by 10 to the negative 12 seconds. We need to divide by the value of gamma they gave us in the question, which was 20. So we get a value of 3.05 by 10 to the negative 13 seconds. You might argue that we should be doing that to 2 sig figs because they gave us gamma as 20. I'm looking at the solutions here and they give this. I'm going to put both because sig figs are important. So that is the lifetime of the tau meson as measured from its own frame of reference. Remember, when you're measuring something within your own frame of reference, you're stationary with respect to that, you're measuring a proper something. Very good. So next asks us, what is the distance d as measured by the scientists? Now, I previously mentioned that this would be the proper length, but the problem is we don't have a contracted length to be able to use our length contraction formula to figure out the proper length. So we're going to need to try a different approach. For these, you're often using speed equals distance over time, but you need to be especially careful about which distances and which times you're using. So I've just written our equation speed equals distance over time and rearranged it for distance equals speed times time. If you find yourself in a situation where you're using speed equals distance over time, you need to use everything from one particular frame of reference. You can't cross-pollinate between measurements from one frame of reference and a different frame of reference. In this example, from the scientists and from the tau mesons frames of references. Frames of references? Frame of reference. You know what I mean. You can't cross-pollinate those. So we need to put in values that are entirely measured by the scientists here. So that distance, well, they measure the speed of the mesons to be that value times c that we had above. Let's look that up. So that was at 0.998749 c. Lots of sig figs there. That was measured by the scientists. And again, the time period measured by the scientists was at 6.10 by 10 to the negative 12 seconds. So let's substitute both of those values back into our equation. So we've got that value times c, and c is that 3.00 by 10 to the 8. And that time we mentioned. Let's get our calc and see what that is. Alrighty. Let's use scientific notation for this, and let's do it for this we can do it to 3 sig figs, so it's going to be 1.83 by 10 to the 1 to negative 3. And the units are not seconds, meters. So that is the distance as measured by the scientists, and let's remind ourselves this is a proper length. We are probably going to now, yes, what is the measured in the reference frame of the tau meson, what would be the distance d? So this is going to be that contracted length. So from the meson's frame of reference, they're going to measure a smaller length that they need to traverse. Here's our length contraction formula that we've been dealing with. We need to put in the value of L0, so 1.83. Let's get a few extra decimals, so 277 instead. ... We'll just use that value in our calculator, and we'll divide it by 20. Okay, 9.14 by 10 to the negative 5. And that's again in meters. So, the biggest difficulty with this question was setting it up really. If you had a diagram similar to this, talking about which times are proper versus the dilated and which lengths are proper versus the contracted, that's really going to help you be able to grapple with questions like this here. I think that was the main thing in being able to unlock this question, because the formulae that you use are relatively simple compared to some of the other ones that we've dealt with in VCE Physics so far. Take a moment to thoroughly read through this question and underline any information that you're able to. If you also feel confident, have a go at identifying any proper values that you might have, and if you've got any contracted lengths or dilated times. Let's see how you go. Okay, I've just put a few annotations here to help me grapple with this really wordy example. That 2.2 micro, is it micro when it's that simple? Yeah, not milli, it's micro, is the proper time in the Muons reference frame. Whereas that length, the height of the mountain, that's the proper length, and I'm referring to the scientist's reference frame here. So that means the Muons will experience a different length and the scientists will experience a different time, that half-life decay time for those Muons here. The experiment is only expected there to be a few Muons being able to reach the ground, but they actually detected many, many more than expected. And then it talks about the reason is, relative to the experimenters, the Muons were moving close to the speed of light, and their half-life as measured by the experimenters increased. So they've given us a nice little diagram here. We've got a whole bunch of Muons. We've got this length here, which I again said that's L0, proper length in scientist's frame. That mountain is not moving. If we've got a little scientist down the bottom here, they're stationary relative to that mountain, whereas the Muons see the mountain flying towards them and past them as they travel towards the ground. So we want to show that the lifetime of the moving Muons as measured from the ground is approximately 2.2 microseconds. So when we say as measured from the ground, we're in the scientist's reference frame. Oh, and I'm very sorry here, I've just noticed an error. That should say 22 microseconds. That's going to be the dilated time here. It couldn't be 2.2 microseconds because then the scientists and the muons would be measuring the same time. My apologies for that error. So we need to figure out what that time is here. But most of the time we see our formula written as such. So rearranging it, it's going to be T0 times gamma. We don't have gamma though, so let's pause on this. We'll determine the value of gamma and then we'll be able to pop it back into this equation here. So we were told they're going at 0.995 c in brackets all squared divided by c squared. So using that trick of leaving it in terms of c, we've cancelled off those values and now let's put that into our calculator. Okay, I get a gamma value of a little bit larger than 10. Remember, there's no units for gamma, it's a dimensionless quantity. So, going back to T equals T0 gamma, T0 was 2.2, let's leave that in terms of microseconds, times 10.01 dot dot dot. They like us to include a couple more decimal places to just really demonstrate that we've done this calculation. So 22.02 dot dot dot, let's do. We're not rounding, but we will round here, equals 22 microseconds. Let's write as required to be fancy. Very nice. So it was really handy not converting out of microseconds in this particular example, leaving it like that because they asked us to show it was approximately 22 microseconds. Okay, this question's really nice. They've tried to make it clear. From the reference frame, the muons see the ground rushing towards them at a speed of 0.995 c. What would the height of the mountain be as measured by these muons? Again, the muons are going to see that contracted length. The proper length was the height of the mountain measured by those scientists. So I'm going to put it on top of gamma here. So those scientists, what did they measure that mountain to be? It was that 2627 meters. And we're going to divide that by our value of gamma. So to be lazy, I just divided what we had by 2.2 to get that value of gamma back. Be really careful with this. You want to be certain you've got the value of gamma now. So if I do answers equal, great, that's fine. So 2627 divided by that value of gamma that we have stored in our answer, 262.37 dot dot dot. And 3 sig figs I think is fine. 262 meters. That's a significantly shorter length here. So that means that the muons, from their perspective, have a much shorter distance to be able to travel. Very convenient. So just going back to this question for a moment, there's two reasons why the muons are able to reach the ground. Number one, from the muons' perspective, they have a shorter distance to travel, or number two, from the scientist's perspective, they have a much larger half-life because it's that dilated time. So there's two reasons, both are correct, but they're just different ways and different frames of references of looking at this question. Let's now do this 2008 Northern Hemisphere question. An alien spaceship has entered our solar system and is headed towards the Earth at a speed of 0.6 c, as shown in the diagram below. When it reaches the distance of 3.0 by 10 to the 11 meters from Earth in the Earth's frame of reference, so that's going to be a proper length then, because the Earth is, in quotation marks, stationary compared to that distance, the aliens transmit a be there soon signal via a laser beam. Ah, very nice. How long will it take the signal to reach Earth according to the observer on Earth? I would argue this one's actually a little easier than some of the things we've done before. So 3.0 by 10 to the 11 meters from the Earth's frame of reference, this distance here. The speed of that laser beam has got to be c. Laser beam is a form of electromagnetic radiation, it's just light, and light always travels at the speed of light regardless of the frame of reference of the observer. So we've got a distance from the Earth's frame of reference, we've got a speed of that light from the Earth's frame of reference, so that's going to help us figure out a time. Let's do that speed equals distance over time again. Time is going to be that distance over that speed. So that distance, 3.0 by 10 to the 11 divided by the speed, 3.0 by 10 to the 8, you could use a little bit of scientific notation or index laws understanding, or you could put that in your calculator and you'll see that it's going to be 1,000 seconds. Really nice. Let me know if you have any questions at all, and good luck with your practice.